All right, so for this problem, there are lots of steps that we're working through here, but really the question is asking us three different pieces. The first one is to sketch the graph, which I have already started for you here. And the second part is to find the area under the curve. That's what this notation means. The area under the curve for the function f of x between 1 and 3. And this should be less than or equal to. We're going to use four left endpoint rectangles to do that, so we'll get to that in a little bit. And then we're going to, the final piece, write the sigma notation expression that represents the area. So to start, I've broken this down into a lot of smaller steps to try and make it a little bit more palatable, but first thing we got to do is find the width of each rectangle. So in this problem here, we're asked to go between 1 and 3, and we're doing four rectangles. Usually the math that I like to do to find the width is just, I know I'm ending at 3, I'm starting at 1, so I subtract them, and then I am breaking it into four rectangles. So when I do that, I get 2/4, which is the same as 1/2, which I'm going to use decimals in these problems here, so I'm going to call that 0.5. So my width is 0.5. And you'll see on the graph I've already kind of done that, where I'm starting here at 1, ending at 3, and then each time I'm going up by 0.5. Second part, plot the points on the graph for 1, 1.5, 2, 2.5, and 3. That's just all these x values down here that we created with my width. So step 2 is to plot those points. If you like tables, great. So for example, if we're plugging in all these x values, we're going to get y values, and I'm plugging it into the equation that we were given. So when I have 1, 1.5, 2, 2.5, and 3, well, I'm plugging those values into 2x plus 1. So 3 plus 1 there is 4. 2 plus 1 is 3. My bad. 2 times 1, and then 2 plus 1 is 3. 1.5 times 2 is 3, plus 1 is 4. 2 times 2 is 4, plus 1 is 5, and you should see kind of the pattern here as you plug them in. So I can actually plot those points here. So 1, 2, 3, 4, 5, 6, 7. So 1, 3, and should be a straight line-ish, depending on how good you are at drawing graphs, but there's our function 2x plus 1. And we're going in between these two lines right here. So step 4 is to draw the four left endpoint rectangles. So here's the first time that the left endpoint piece comes into play. Left endpoint means that it's going to be, each endpoint that we use is going to be the left side of my rectangle. For example, my first one here, I go up to this first point and then I go straight across and down. My second one, I'm using the second point here, and because it's the left side of my rectangle, straight across and down, straight across and down, straight across and down. So if you notice in the red here, I have four rectangles, and each of them, the side that I use that is actually touching my function is the left side. That's what left endpoint means. If it were right endpoint, then the right side of the rectangle would actually touch the function. Okay, label your x values with numbers and subscript notation. So that one I have actually already done here in purple. That's something that I did for the first one to give you kind of an example of what it looks like. Here are my x sub numbers, so my subscript notation, and here are all my x values. The reason that's helpful is that because for step 5 here, we'll do in orange, is to create a table for your subscript notation. So what that means is that, x of 0, all these little numbers here, we're going to call those k values, and then x of that number just gives us these specific x values. So what I mean by that is x of 0, so when k is 0, is equal to 1. X of 1, or when k is 1, is equal to 1.5. So I'm really just matching up the k values here, 3 and 4, and my x values, which 2, 2.5, and 3. to create a second table for this equation. And the reason we come up with this table is because when we create sigma notation, when we do this part here, x is not always the same value. So I can't just plug in x. I have to actually come up with an equation for that, x sub k. And so I'm going to do that for step 6, and just know that step 5 and 6 are not for area under the curve, but for sigma notation. So I can see that it's going up by 0.5 each time. So x of k equals 0.5 times k. And then when k is 0, x of k is 1. And that's how I create my linear equations. The x sub k is always going to be a linear equation, by the way, because our width is always going to be the same. The other thing is that our width is always going to be that coefficient there in front of k. Okay, back to area under the curve. So I'm going to zoom out of here so we can see our graph still. So step 7 here says find the height of each rectangle. We kind of already did that with this table right here. So really what you should see here is that the heights, again, are represented by the left side. So when I plugged in 1, I got 3. So this height here is going to be 3. When I plugged in 1.5, I got 4. When I plugged in 2, I got 5. And 2.5, I got 6. So those are all the heights of my rectangles there. So step 8, I'm just doing the widths times the heights because there's 4 rectangles, so I have to do all of those. So 0.5 times the first height, which is 3. And then I'm going to add all of these together in the end because all of the rectangles combined are going to be what give me my full area under the curve. So 0.5 times 4, 0.5, let's see if I have 3 over here, times 5. And again, these are just because those are my heights for my rectangles over there on the left. And my last one, 0.5 times 6. So when I multiply all of these together, right, I could do this one at a time. I could say, this is 1.5, this is 2, this is 2.5, and this is 3. So those are all the areas of my 4 rectangles. Note that I only have 4 values. If the big mistake that people make is that they use this value here as well on the right side of my graph, which not good because we're not going to need 5 values. We only need the 4 rectangles that we created. And this brown side that I just created here is the height of none of my rectangles, so it doesn't help me. So now when I add all these together here, I get 5, 6, 7, 8, 9. So my area under the curve, my estimate here is 9 square units. Okay, for step 10, plug in pieces for sigma notation, width and height. And I'm going to talk kind of through this because I have this one actually already done for you. So for sigma notation, what you got to know is that when we're using the left endpoint rectangles, we're always starting at k is equal to 0. And because if you notice here, let's erase some of this to give me a little bit better of a view here. So I got lots of arrows and stuff. So I have these rectangles here in red, and the heights, what you should notice here, that I'll do in light blue here, the heights are only using, 4 sides. So I really only use x of 0 all the way through x of 3, which is why in sigma notation I have k equals 0 and k equals 3, because that right there is telling me which k values I'm going to use. The width we found, the first thing was that it's 0.5. Width is always going to be the same for each of the rectangles, and that's kind of my first step. And so I find 0.5 there. Then for the height, well, I have 4 different heights, which is why I have to use an equation. And I'm going to use the original equation that we were given, where we had f of x equals 2x plus 1. So I'm plugging that in for height. The only difference is that I need another equation within f of x, because remember, we're using 4 different x values in this. So we're going to throw in the equation that we created, x of k, that we created earlier, and we're going to put that within our function f of x. So my final answer here, when I've plugged everything in, is going to be k equals 0 on the bottom, 3 on the top, because that's where we're going from. 0.5 is our width, And then our height here is our original function with x of k plugged in for wherever x was at. Now, technically, could you distribute this and simplify? Yes, but I'm going to leave it as is for now and call this good for our final answer.